Hi all. In our last section on 1.4, we were looking at efficiency and how good something is at converting input energy into desired output energy. Again, remember 100% of energy in comes out, but it's not all desirable. It's not all in a form that is useful. So if we look at the questions that we had from the homework, I had left you with these questions here from our textbook. And a couple of them are a little bit tricky. They need us to do the 1.5 note before we can actually do, say, question 45 there. I'm going to come back to that one maybe at the end of this note here for 1.5. Now, maybe I will start with one of the review questions here. I'll start with question 3 for 1 point in the review for 1.4. So if I look at the review for 1.4, there's question 3 right there. And it says, a golf club has 65 joules of kinetic energy, which is going to hit a golf ball. The golf ball has a mass of 46 grams, and the energy transfer is only 20% efficient. So the energy that went in from the golf club, only 20% of it is going to be used to create kinetic energy in my golf ball. The question is, what will be the speed of the golf ball? Now, if I look at the question, here is the golf club, and it's got the input energy that's going to be driving that golf ball at 65 joules. Here's the golf ball that's ultimately going to end up with kinetic energy, which is my desired output energy. Okay, that's desired energy out, right? And that's going to be equal to a half mv squared. And I know that in this energy transformation of kinetic energy from the club to kinetic energy of the ball, it's only 20% efficient. So before I can do anything, I'm trying to figure out what will be the speed of the golf ball, right, when we're done. Now to do that, I need to know my energy out from the energy transformation. So if I know that my percent efficiency, is equal to my desired energy out divided by my energy in times 100%, and I know that my efficiency here is 20%, my energy out is unknown, my energy in was 65 joules. Okay, so what I'm going to do now is take my 100 under the 20, so I've got 20 divided by 100, which is 20%, times 65, and I get an E out of 13 joules. So that's how much energy the golf ball is going to have when it leaves the club, right? Only 13 joules. Even though the club had 65, only 20% of that was converted into kinetic energy of the golf ball. Now, I know that the kinetic energy here is equal to 1/2 mv squared, because the 13 joules here is kinetic energy, right? The energy out that I'm looking at is actually kinetic energy. So, if I know that my energy out down here is kinetic energy, and it's 13 joules, I can now substitute in the mass of the golf ball, 1/2 of 46 grams, 0.046 kilograms, times v squared. Remember, mass has to be in kilograms for half mv squared. And when you do the math, I'm getting a speed of the golf ball of 24 meters per second, which is about almost 90 kilometers an hour. Right? So the golf ball is moving pretty fast after it gets hit by the golf club. Okay, so there is one of the homework questions from last night, from yesterday. Okay, today I want to move into our second last topic, just a short topic, but a really important topic, and that's the concept of power. Now, we've been talking, again, for almost a week now about energy transformations. We said energy can be transformed from one form to another, right? But it's not an instantaneous thing. When energy gets converted from electricity into, let's say, height in an elevator, right? If I've got an elevator car at the ground level and the electricity is going to rise it up to the 7th floor, right? That gravitational energy, it took time for that to happen. So our definition for power is how fast energy is being transformed. In other words, take the energy transformation and divide it by the time, and that gives me the power that has been used. Now, because energy is measured in joules, right? Energy here is measured in joules, and time is going to be measured in seconds. The units here are joules per second of energy transformation. How many joules are transformed per second? Now, because our units are in joules per second, again, we're going to name this after another famous physicist, and our new units are going to be called watts. Okay, so a watt is what is happening when 1 watt means 1 joule of energy is being transformed per second. Now, if a power level is high for a device, that means typically a lot of energy is being transformed in a small amount of time. Now, we've already looked at what happens when energy is transformed. We called that work back in the early part of this section 1. So power can also be described as work per unit time. I would say most of the time when I'm using this formula, I'm using it this way, but it also can be used in this format too, because W is also defined as delta E. So if I look at the sample for 1.5a here, there's two sample problems. First one says, how much power does a swimmer produce if she transforms 2.5 kilojoules of chemical energy, okay, that's food, chemical energy, into kinetic energy in 12.5 seconds. So as she is swimming, she's creating speed, and she's creating heat, right? And those two things are going to be the output energy from her input energy, which is food. So I'm not looking at how efficient this is. All I'm looking at is how fast is her food being burned. So to calculate the power here, it's going to be the energy transformed divided by the time it takes for the transformation. Right? I know that she is swimming and using 2.4 kilojoules, or 2.4 times 10 to the power of 3 joules in 12.5 seconds. So we're seeing that she has a power rating of 190 joules per second, right? Joules per second, or 190 watts. Okay. The second question here is one that I do every semester when I'm at school. You could probably do this on your own. If you wanted to figure out your own power consumption, if you've got a set of stairs that you can climb somewhere, you can calculate your mass, step on a set of bathroom scales to find your mass. If your mass is in pounds, you can divide by 2.2 to get kilograms. And then once you know how many kilograms, calculate how high one step is, let's say in your house or your apartment building, and then count how many steps there are. So if a stair is 17 centimeters, then you're going up 10 stairs, then you're going up 170 centimeters. So multiply the number of stairs times the height per stair. That will tell you the height that your body's going to move, and then figure out how long it takes you. So use your phone to calculate the time that it takes to go up, given your mass, and to calculate how high you're going to go also. So for power, I'm going to figure out how much energy is going to be produced in how much time. Now, you can see here that what we're doing is we're creating gravitational potential energy. So I don't think maybe I'll just erase this. So for problem 2 here, the question is, what is the power? Well, I need to know what is the energy here. The energy here that's being created, always, the easiest way to solve this problem is to say, what am I doing? Well, I'm going up. I'm generating gravitational energy. What was she doing? She was using up food in the previous question, right? So always look at what is happening in the question. So in this case, this person is with 64 kilograms of mass on Earth, 9.8, is traveling to a height of 3.7 meters. Okay, and I'm going to get a gravitational energy of 2.32 times 10 to the third joules. Okay, now I know my energy and my time is given in the question. I can solve for my power. So power is going to be 2.3 times 10 to the third joules divided by the time of 5.5 seconds. Okay, you can see that if the shorter the time, the greater the power rating, because time is in the denominator. The smaller the denominator, right, the faster will be my greater will be my power rating. So I'm going to take my 2300 joules divided by 5.5 seconds, and I'm getting 418 watts, or 4.2 times 10 to the second watts. Now, if you decide to go up the stairs, and maybe you get up those stairs in 3 seconds, right, your power now goes up to more like 800 watts. If you could do it in a second and a half, maybe your power goes down to well over 1,000 watts, right? But the faster you go up, the harder your heart's going to be pumping when you get to the top, because you've had to use that much power. In other words, you're burning energy so fast that your heart's got to allow for that to happen. Okay, so you can see that there are a couple of sample problems here, 1, 2, and 3. Okay, so these are these questions here, 1, 2, and 3. And then there are some examples here at the end of our textbook on pages. There are 2 that are done for you here on page 222. And then there are some at the end of the chapter for you to practice. Now, I said I was going to go back and look at question 47 here back in our textbook. So I'm going to go back to question 47. Sorry, it wasn't 47, it was 45. In our textbook on page 244. Now, it talks about a water pump running to send water up to the top of a water tower. So if you go driving out of Hamilton, let's say you go driving down through Dundas, you'll see the Dundas water tower, right? It's a big... and it says Dundas on the top. If you go to Caledonia, you'll see the Caledonia water tower. If you go to Hagersville, you'll see the Hagersville water tower. And what happens is, all the homes that are down here in Dundas, right, are sleeping at 4 a.m. At 7 a.m., everyone wakes up and starts getting ready to go to work, and they start having showers and doing some dishes and maybe putting on a load of laundry that they forgot to put on last night, and maybe washing their car before they go to work. Whatever happens, these people need a lot of water. right? And the water basically typically comes from underground, but there are so many people needing water at the same time that what happens is during the night, the city of Dundas pumps water from the ground up into the water tower, and they fill the water tower with water. So in the morning, when all these people are trying to get the water that they need, they get some from under the ground, but they also take some of the water that was up in the water tower. So the question here is talking about using a pump to get water up into the water tower. Now, let's get rid of some of my artwork here. Okay, so what we're told in the question, okay, we're told the water pump has a power rating of 750 watts. And we're told that the water pumps 1.48 kilograms of water per second. 1.48 kilograms per second. And that we know that the height that it's got to travel is 37 meters. So let's just take a step sideways here and say, what is 750 watts? Well, we know that 750 watts is 750 joules per second. That's what a watt is, right? It's 1 joule of energy used per second by that pump, right? That's the electricity that's going into the pump to run it. So if I just say, what happens in 1 second? I'm going to take 1.48 kilograms of water, and I'm going to move it to this height here. So there's my gravitational energy, right? That's my desired output. What am I doing? I'm trying to move water. So my desired energy output E out is the gravitational energy of the water, which we know is mgh. Now, my desired energy out, if I know that in 1 second I move 1.4 kilograms of water on Earth in Dundas to a height of 37 meters, I can calculate my gravitational potential energy, that is my desired output. That's why I bought the pump. And I'm getting 537 joules is the energy out in 1 second. Now if I say, what was the energy input? Well, the energy input, if the pump is using 750 joules per second, that means in that 1 second that it was running, I used 750 joules of input energy to move the water up the pump. Now I can also calculate that amount. I can say the energy in is equal to power times time, because remember, power equals energy over time. So the energy in is going to be my 750 watts times 1 second, which is 750 joules. So now I know my energy in and I know my energy out. I can calculate my efficiency for this pump. So the efficiency percent efficiency is desired energy out divided by my energy input times 100. My desired energy out, we know up here, was 537 joules divided by my energy in, which we know over here was what the pump was using, 750 joules times 100, and I'm getting 537 divided by 750 times 100 is 72%. Okay, so now we're using our efficiency equation with our MGH up here, along with our power equals energy over time here, all to solve Dundas's water problem. Okay, so I'm going to stop there. I've got one last topic to cover in one last note, 1.5b, and that will be looking at how much it costs for electricity. Okay, so there are some questions on power. I've already looked at those here on page 242 of our textbook, and on the examples that were done for you. Again, I encourage you to do them on your own first, and then go back and double check to see how they did them.